Testing, can you hear me? Testing again. We should mention that x86 processors have an op instruction that does not do anything at all. I'm just reading a random text. All right, this video is public now, so I am going to be reading computer architecture again. I will just continue from where I left off. Mhm. Okay, hold on, let me change to full screen. All right, so last the last thing I learned was the instructions enter and leave. So enter, we save like some number of bits for the activation block. And then when we are done, we use the leave function to go back to this call line. Okay, anyways, advanced memory instructions, string instructions, semantics. Okay. The LEA instruction stands for load effective address. It has a register operand and a memory operand. The role of LEA instruction is to copy the address of the memory operand to the register. So memory is described here and it goes to the register. So EBX saves the address of the register, right? Let us now introduce a special set of instructions known as string instructions, which are introduce the following instructions: stores, loads, and moves. The stores instructions transfer data from the EX register to the location specified by the EDI register. From EAX to EDI to whatever is stored in EDI. What was the meaning of EDI again? Let me see. DI. Is it destination index? Base pointer? Yeah, destination. Okay. So we assume the register is stored in the destination index. Wait, where was I? Enter and leave. Okay. So from EAX to whatever destination index is here, source index, and then the load does the opposite. So source index to EAX. Comes in four flavors depending upon the amount of data that we wish to transfer. It uses the B suffix for 1 byte, W for 2, and then double word, and then quadruple word. We show an example of STD, so stores D instruction in table 5.18. Okay. And then EDI, it increments, right? Not increments, it's like goes to the next memory. Stores is the stores D instruction transfers the contents of EAX 4 bytes to memory address specified by EDI. Subsequently, this instruction increments or decrements the contents of EDI by 4 depending on the direction flag. Depending on the direction flag. Okay. So either go for forwards or backwards. Uh, okay. The direction flag is a field in the flags register similar to zero carry and overflow. If the direction flag is set to 1, then that stores instruction subtracts the size of the operand from the contents of EDI. He introduced two zero address format instructions, namely STD and CLD, to set and reset the direction flag respectively. STD and CLD. So what does STD and CLD stand for? The load S and move S set of instructions are defined similarly. For example, load SD instruction transfers the contents of memory locations specified by ESI, so source index, to EAS. It subsequently increments or decrements the contents of ESI by the size of the operands based on the value of DF. The move S instruction combines the functionality of load S and store S. Reverse fetches a set of bytes from the memory address and stored in ESI. Subsequently, it writes the bytes to the memory address specified by EDI. Increments and decrements ESI and EDI, source index and destination index based on the value of the direction flag. So move SD. So move, okay. So move SD, it moves whatever is stored in the source index to the destination index. And it increments or decrements them. The SI register stands for source index register. And DI stands for destination index. So stack pointer plus 4 stored in destination index. Move 21 to AX, store D, so double word, saves EAX in EDI. A word is 2 byte, right? Yeah. EDI. And then move ESP plus 4. So 21 goes to ESP plus 4. And then the memory in ESP plus 4 then goes to EBX. So EBX has 21 now. What is the value of EX after executing this code snippet? Move double word 19 goes to here. And then load TS. So source index to EX. What is the value of EX? They move 19 here, right? LE, what is LEA again? LEA from here to here. LEA from here to source index and load what is stored in source index then goes to EX. And in that memory address, we store 19 and source index stores that memory address. So whatever is stored in that memory address, then it goes to EX, which is 19. Okay. Instructions with the rep prefix. The string instructions can additionally increment or decrement the values of ESI, So source index and destination index, we have not used this feature up till now. Let us use this feature to transfer an array of 10 integers from one location to another. This feature is very frequently used in modern processors to transfer large amounts of data between two locations. Write a program to create a copy of 10 element integer array. Assume uh, assume that the starting address of the original array is stored in source index. Starting address of the destination array is stored in destination index. Mm. Yeah, so 0 is EBX. Wait. ESI EBX times 4. Okay, this is the index. Right, so whatever is stored in this memory address goes to EDX. And whatever is stored in EDX goes in this. Okay, I understand. We are copying from ESI to EDI. Then increment EBX. Wait. ESI times 4. Why are we doing times 4 again? So if this was 1, you would have 4, 4. If this was 2, you would have 8, 8. This was 3, we would have 12, 12. Okay, okay, now I understand. Yeah, yeah, yeah. 4, 4. Um, the memory address takes 4 bytes, right? Write a program to create a copy of a 10 element integer array. Assume that the starting index of the original array is stored in ESI. Starting index of the destination array is stored in EDI. Use the move SD instruction. Move SD copies whatever stored in the source to destination, right? So wait. We use the load, not load, it's already in. We just have to use move S 10 times, right? And it will just do this and increment on its own. Answer CDF is equal to 0, move 0 here. Move SD, increment EBX. Compare, okay, this is to make sure we do it 10 times. In example 83, we use the move SD instruction to replace a pair of load and store instructions with just one instruction. This reduces the number of instructions in the loop from 5 to 4. We were not able to get a bigger reduction because we still need to update the loop index and compute the loop condition. To make our code look even more elegant, the x86 defines a rep prefix that can be used with any string instruction. The rep prefix instructs the processor to execute a single string instruction n times, where n is the value stored in ECX register. Every time the processor executes string instruction, it decrements ECX. At the end, the value of ECX becomes 0. Its semantics is shown in table 5.19. Rep instruction rep move SD. Okay. So whatever is stored in ECX, like ECX, if it stores 10, we can decrement. So first ECX 10 and then rep move SD. Rep prefix thus allows us to fold an entire loop into just one instruction, as shown in example 84. The rep prefix is meant to be used with string instructions for copying large regions. They should uh, they should have had another argument where the number of loops is stored in a register. It should take rep should take another operand that stores the count. So instead of rep move fc, it should be rep esx move st. This way we can specify our own register. The rep instruction also has two variants, namely rep e and rep ne. These instructions use an additional termination condition along with the value of ECX. Instructions prefix with rep e can also terminate with when the zero flag becomes zero. And an instruction prefix with rep ne also terminates when the zero flag becomes 1. Rep equal and a rep not equal. x86 has a large set of floating point instructions. Let us first give a historical perspective. The early 8086 processor and many of its successors did the Intel 486 did not have a floating point unit in the processor. They used a separate coprocessor chip called the x87 that provided floating point capability. However, after the release of Intel 486, the floating point unit has been an integral part of the x86 architecture. Hence, many features of the floating point ISA are artifacts of the older era, in which a floating point instruction was essentially a message to the external processing unit. One of the direct consequences of such a design strategy is that there is no direct communication paths between integer registers and floating point registers. Secondly, it is not possible to load an immediate into a floating point register by specifying its value in an instruction. I can load values into a floating point registers only via memory. For example, if we wish to store a floating point constant in a floating point register, then we need to first load the constant in memory. Subsequently, we need to issue a floating point load instruction to load the constant into a floating point register. Figure 5.3 shows a conceptual organization of the x86 ISA. The integer instructions use the integer register and they have their own processor state. Likewise, the floating point instructions use their set of registers and have their own state. Both the type of instructions, however, share the memory. Let us start by looking at methods to load values into the floating point registers. We should refer to the floating point register stack as the FP stack and designate the floating point registers T0 to T7 as rich while describing the semantics of instructions. We should also abbreviate the floating point as FP for the sake of brevity. So load instructions, FLD min, FLD rich, and FLD mem. Pushes the FP number stored in EAX to the FP stack, pushes the contents of ST1 to the top of the stack, and pushes the integer stored in EAX to the FP stack. Or FILD, after converting it to a 32-bit floating point number. Okay. Pushes an FP number stored in the memory address EAX. And FI, it pushes an integer. Table 5.2 shows the semantics of a floating point load instructions. The most commonly used floating point load instruction is the FLD instruction. The first variant of the FLD instruction can load a 32-bit floating point value from memory and push it to the FP stack. We can use our standard addressing modes with integer registers as described in section 5.2.4. Specifying an address in memory, the second variant can push the contents of an existing FP register on the FP stack. You can alternatively use the FILD instruction that can read an integer from memory, convert it to floating point, and push it on the FP stack. Let us consider an example. Push the constant 2.392 on the FP stack. We need to first define the constant 2.392 in the data section. In NASM, we do this as follows. Section data num dd 2.392. You need to embed this code snippet at the beginning of the assembly file. Here, declaration section.data means that we are declaring the data section. The data section, we further declare a variable num that is a double word specified by dd, and its value is 2.392. Let us now push the value of the f to the fp stack. We need to embed the following code snippet in the main assembly function. The assembler treats num as a memory address. While generating code, it will replace it with its actual address. However, in an assembly program, we can seamlessly treat num as a valid memory address, and its content can thus be represented as num. Well, the address stored in num. The FLD, not address. Num is an address. When you dereference num that. The FLD instruction in this code snippet loads 32-bit from num to the top of the FP stack. FLD from num to the top of the FP stack. And num is mentioned in the data section, right? Exchange instruction. Table 5.21 shows the format of the floating point exchange instruction FXCH. It exchanges the contents of two floating point registers. Given address format exchanges the contents of the registers specified as the first operand and ST0. Okay, ST0 and ST3. Otherwise, FXCH with no operand, it will switch ST0 and ST1. Store instructions. F store mem, F store register, F store mem. No, F stack pointer, right? Let us look at how store instructions in table 5.22. Let us look at the store instructions in table 5.22. Format is similar to the floating point load instructions. ST0 goes here, ST0 goes here. Register memory, stack pointer. So from T0 to EX, pop the FP stack. ST0, F integer store, T0 to here, to the memory stored in EX. ST0 to here, and then pop the so F store pop. F integer store pop. Third, first variant requires a single memory operand. It stores the contents of the ST0 in the memory location specified by the memory operand. Second variant requires an FP register operand and stores the contents of ST0 in the FP register. Third variant uses the P suffix, which is generic suffix and is used by many other instructions also. The FSTP instruction initially saves the value contained in ST0 in the memory location specified by the first operand, then pops the stack. Since the stack size is limited, it is often necessary to pop the stack to create more space. We are storing ST0. When you are storing ST0, we are saving a copy of its contents in main memory. Hence, it makes sense to have a variant of the FST instruction, fstore instruction that can free the entry from the stack by popping it. x86 has additional support for conversion of floating point values to integers. We can use the FIST instruction that first converts the contents of ST0 to a signed integer by rounding it and then saves it in the location specified by the memory operand. Note that we will always use a modifier for memory operands such that we can specify the number of bytes that need to be transferred. The FIST instruction also supports P suffix semantics of the FISTP instruction in table 5.22. Let us now consider arithmetic instructions. Floating point ISA in x86 has a rich support for floating point operations and is thus extensively used in numerical computing. Let us start with the basic floating point add instruction and take a look at all of its variants. We can add what is stored in memory, add register to register. Okay. So what is stored in memory goes to ST0. And then F add pop. You can add ST1 to ST0 and pop the FP stack. What if we do F add pop ST0? What happens then? F integer add mem. So what is stored in EX gets converted to a float plus ST0 goes to FT0. The semantics of the floating point add instructions is shown in table 5.32. The basic FR instruction has two variants. The first variant uses single memory operand. Here we add the value of the floating point number contained in the memory location to the contents of ST0. The result is also stored in ST0. The second variant of the if add instruction uses two floating point registers as arguments. It adds the contents of the second register to the first register. The fadd instruction follows the same pattern as the floating point load and store instructions. It accepts the p suffix. The fadd p instruction typically takes one argument, which is a register. We show an example of the instruction fadd p st1 in table 2.5.23. Here we add the contents of ST0 to ST1 and save the result in ST1. ST0, ST1, save it in ST1. Then we pop the stack. For working with integers, we use the fi add instruction that takes the address of an integer in memory. It adds this integer to ST0 and saves the result in ST0. x86 defines subtraction, multiplication, division instructions that have exactly the same format as fadd instructions. F sub mem. Okay, F mem, F divide mem, and it will have the same variants as well, right? So pop and then the integer add. So what is we are doing integer load, right, over there? Yep. F load, integer load, add, divide. Compare the arithmetic mean of two integers stored in EX and EBX. Save the result in ESP plus 4. Assume that the data section contains the integer 2 and the memory address 2. So move EAX to ESP stack pointer, and then EBX goes to the next value in the stack. Wait, why are we using floating points? Arithmetic. Okay, it's an arithmetic mean. Floating point integer add what is stored in ESP. And then over here, what is stored in ESP plus 4. Wait, when we are doing integer, we can't address a register with this. So first we have to save it in memory and then register, right? And then sorry, we have to save it in memory and then address the memory, right? Add these two. F add ST0, ST1. Shouldn't we pop it as well? F divide in address 2. This is in the data section. Then F store pop keyword ESP plus 4. Save the result in ESP plus 4. Okay. Instructions for special functions. F absolute. It has its own square root function. F cos. F, how is the square root, cos, and sine? How are these calculated? The richness of the x86 ISA is that it supports trigonometric functions and complex mathematical operations such as square root and log operations. The f absolute function computes the absolute value of st0 and the f square root function computes the square root. The f cos and f sine function computes the sine and cos of the values stored in st0 respectively. All of these instructions use st0 as the default operand and also write the result back to st0. Wait. So all of these instructions, they only use, are there variants of these instructions like there were with the other ones? So F compare register, compare ST0 and compare ST1 and set the E flags register. F compare I pop ST0 and ST1, set the E flags and pop the FP stack. Wait, hold on. Why do we need a separate compare just for the floating points? Aren't we still checking whether the ones and zeros are the same? As the x86 ISA has many compare instructions. In this section, we should present only one compare instruction called F compare I. What's with the I? It compares two floating point values, saves in register and sets the E flag registers. With and without the P suffix. Once the E flags register is set, we can use regular branch instructions for implementing control flow within the program. Note that in x86, we need to use the condition codes for unsigned comparison in this case. Most of the time, programmers make the mistake of using condition codes for signed comparisons such as L, LE, G, or GE for testing the results of floating point comparisons. This leads to the wrong result. We should instead use the A above and B below condition codes. So less than or equal to, greater than or equal to is used for is used for integers, but above and below is used for floating points, right? Okay. Compare sine 2 theta and 2 times sine theta cos theta. Verify that they have the same value for any given value of theta. Assume that theta is stored in the data section at the label theta, and the threshold for floating point comparison is stored at label threshold. Save the result in EAX. So float lower theta. Wait, where are we loading? We are loading it to ST0. Load theta. Load theta. LEA, no, convey to up. F load pushes an FP stack stored in EAX to the FP stack. Oh no, it puts this to the FP stack. F add, so go to the FP stack. So store it in the FP stack. F add ST0. ST0, okay, theta plus theta. F sign. Okay. Stack pointer. Store pop. What's stored in ESP? Oh, we are saving. No, wait. Sign. Yeah. We are saving sine 2 theta in ESP. Now, float load theta. Okay. Float store ST1. Okay, so what is stored in ST0 goes to ST1. That's what it's doing, right? And then do sign with the ST0 and do exchange. Then do cost with ST0. F mul these two. Then F add, so you double the value. So before we stored it in ESP, don't we need to store this in ESP plus? And then next, like ESP plus 4. Compute the modulus of the difference. F load. So ESP, subtract T0 and T1, and then take the modulus. And how do we compare? And we load the threshold, compare I, ST0, and we check if it's below the threshold, right? So if it's above, no wait, above or below? Threshold. It has to be below the threshold, right? Move EAX 0. Jump to exit. And jump if above equal EX stores 1. Wait. Jump if above. We use the above and below condition codes. Jump if above the threshold. When we compare them, the compare function actually subtracts them, right? And it sets the above or below flag. Above or below low threshold. Threshold is stored in ST0. If the threshold is greater, okay, yeah. That makes sense. If the threshold is greater, then they're equal. Okay. F free reg, free ST4. F init, reset the status of FP unit, including the FP stack and register. Table 5.75 shows two instructions for cleaning up the FP stack. The F free instruction sets the status of the register specified as an operand to empty. Using free to free all the registers is a quick solution. For freeing the entire stack, we need to invoke free instruction iteratively. For deleting the entire FP stack, a cleaner solution is to use the init instruction that does not take any argument. Resets the FP unit, frees all the register, and resets the stack pointer. The init instruction ensures that an unrelated function can start from a clean state. We have taken a look at a wide variety of x86 instructions addressing modes and instruction format. It is truly a complex instruction set. However, the process of encoding is more regular. Almost all of the instructions follow a standard format. In this case, in the case of ARM and Super RISC, we described the process for encoding instructions in great detail. We shall refrain from doing this here for the sake of brevity. Secondly, an opcode in x86 typically have a variety of modes and prefixes. We do not need to digress from the main theme of the book by describing x86 in such level of detail. Let us start by looking at a broad structure of an encoding machine instruction. So we have a prefix, opcode, mod, displacement immediate, SIB. The first 1 to 4 bytes are used to encode the prefix of the instruction. The rep prefix is one such example of a prefix. There are many other kinds of prefixes that can be encoded in the first group of 1 to 4 bytes. The next 1 to 3 bytes are used for encoding the opcode. Recall that the entire x86 ISA has hundreds of instructions. Secondly, the opcode also encodes the format of the operands. For example, the add instruction can either have its first operand as a memory operand or have its second operand as a memory operand. This information is also a part of the opcode. The next two bytes are optional. The first byte is shown as mod r/m byte, which specifies the address of the source and destination registers. And the second byte is known as the SIB byte. This byte records the parameters for the base scale index and the base scale index offset addressing modes. A memory address might optionally have a displacement that can be as large as 32 bits. We can thus optionally have 4 more bytes in an instruction to record the value of the displacement. Lastly, some x86 instructions accept an immediate as an operand. The immediate can also be as large as 32 bits. Hence, the last field, which is again optional, is used to specify an immediate operand. Let us now discuss mod RM and SIB bytes in more detail. Mod RM has 3 fields. The two most significant bits contain the mod field. The mod field indicates the addressing mode of the instruction. It can take 4 values as shown in table 5.228. Mod bit 00011011. Register encoding. There are 8 of them, right? We use the register indirect addressing mode for one of the operands. When RM is equal to 100, we use the base scaled index addressing mode and there is no displacement. Wait, let me see. We take 4 values. The mod field indicates the addressing mode of one of the operands. It can either be a register or a memory operand. If it is a memory operand, then we have 3 options. We can have either no displacement, an 8-bit displacement, or a 32-bit displacement. If it is a register operand, then the mod field has the value of 1, 1. The important point to note is that all of the memory address modes. The important point to note is that for all of the memory address modes, if the RM bits are equal to 100, then we need to use the information in the SIB byte for computing the effective memory address. Let me see. When RM is equal to 100, we use the base scale index addressing mode and there is no displacement. The IDs of the scale index and base are specified in the SIB byte. When RM is equal to 101, the memory address only consists of the displacement. The rest of the values of the RM bits specify the ID of the base registers shown in table 5.29. Other than the case of RM101, the rest of the combinations of the RM bits are not associated with the displacement. We use a single byte side displacement at 01. If RM is equal to 100, then we get the IDs of the base and index registers from the SIB byte. If it's 10, we use 4 byte side displacement. If RM is 100, then we get the IDs of the base and index registers from the SIB byte. And then 11 is register direct addressing mode. The SIB byte is used to specify the base and index registers, possibly with scaling. For example, it can be used to encode memory operands of the form EAX plus ECX times 4. Recall that to use the SIB byte, it is essential to set the mod field in the mod RM register to 100. This indicates to the processor that the SIB byte follows the mod RM byte. Structure of the SIB byte is shown in figure 5.6. Scale, index, base. Oh, that's what SIB means. The effective memory address before considering the displacement is equal to base plus index times scale. The base and index fields point to integer registers. Both of them are 3 bits. 3 bits each. And use the encoding shown in table 5.29. The two most significant bits are used to specify the scale. We can have 4 values for the scale in x86 instructions, namely 00, 01, 10, and 11. Note that some rules need to be followed while encoding memory operands. The ESP register cannot be an index, and if the value of the mod field is 00, then EBP cannot be a valid base register. Recall that if we set the RM bits to 101, when the mod field is 00, then the memory address is only a displacement. Or in other words, we can use memory direct addressing by directly specifying its address. If mod is 00, then in the SIB byte, EBP cannot be a valid base register. We specify the base register as EBP in the SIB byte, then the processor calculates the effective memory address based on the value of the scale and the index. Encode the instruction add EBX, EDX, ECX times 2 plus 32. So, wait, this is the base, index, scale, offset, right? Assume that the opcode for the add instruction is 03. Let us calculate the value of the mod RM byte. In this case, our displacement fits within 8 bits. So wait, let me see that again. Register indirect addressing mode. Single byte signed displacement, 4 byte signed displacement. Register indirect addressing mode for one of the operands. When RM is equal to 100, we use the base, scale, index addressing mode, and there is no displacement. Hence, we can set the mod bits to 01 corresponding to an 8-bit displacement. We need to use the SIB byte because we have a scale, okay, and we have an index. Scale, index, base. Thus, we set the RM bits to 100. The destination register is EBX. Its code is 011 according to table 5.29. Thus, the mod RM byte is 0101. Wait. 01011100. No, wait. Where is this 011? Okay, wait. So 01 is the mod bit. 011 is the destination, right? Then 100 is the RM bits. But is it in the mod first? No. Yeah, mod register RM. Okay. Now let us calculate the value of SIB byte. The scale is equal to 2. Thus, as it is encoded as 01, the index is ECX, which is 001. The base is EDX, which is 010. Hence, the SIB byte is 010011010, which is 4A. The last byte is the displacement, which is equal to 20. The encoding of the instruction is 035C4A20 in hex. All right. Yeah, I will read the summary and then I will end the stream. The x86 ISA is a family of the complex instruction set that is primarily used by Intel and AMD processors. The original used 8086 processors used a 16-bit ISA. Since the mid-80s, moved to 32 bits, and since 2003, we have 64 bits. Basic instructions of all ISAs is the same. There are minor differences in the syntax. The 8 basic registers is AX, ABCD, stack pointer, base pointer, source index, and destination index. Use E prefix in this 32-bit mode and R prefix in the 64-bit mode. And the 16-bit ISA has the IP register to save the program count and the flags register to save the result of the last comparison and other fields that instructions may use. The x86 predominantly uses instructions in two address format. First is typically both the source and the destination. Secondly, one of the operands can be a memory operand. It is thus possible to fetch the value of the memory location, operate on it, and write it back to memory in the same instruction. x86 processes see a segmented memory model. Entire memory space is partitioned into different segments. Instructions reside in the code segment by default, and data resides in the data or stack segments by default. It is in general not possible for instructions to access segments that they typically are not meant for. Is that why we get like the seg fault when we code in C? For example, it is generally not possible for a store instruction to change the contents of an instruction in the code segment. In the 16-bit mode, the top 16 bits of the starting address of each segment are stored in the segment register. The effective memory address specified by an memory instruction is added to the address contained in the segment register to compute the actual memory address. In later ISAs, the contents of the segment registers are looked up in the segment descriptor tables. For obtaining the starting address of segments, to speed up memory accesses, processors typically use a small memory structure known as a segment descriptor cache that keeps the most recently used entries. x86 integer instructions. The move instruction is one of the most versatile instructions. It can move values between two registers or between registers and memory addresses. It can also be used to load immediates in the registers or memory locations. x86 defines a host of other arithmetics and branch instructions. String instructions are unique features of the x86 ISA. They can be used to transfer large amounts of data between memory locations. To compress an entire loop of string instructions into one instruction, we typically use the rep prefix that repeats a given instruction in n times, where n is the value stored in the ECX register. The x86 floating point registers can either be accessed as normal registers or as values or on a floating point stack. Most of the floating point instructions operate on ST0, which is the top of the stack. There's no direct way to load immediates into the FP stack. We need to first load them into memory and then load them to the floating point stack. x86 has instructions for computing complex mathematical operations and trigonometric functions directly. They use the Taylor series, right, for computing the trigonometric function. Encoding the x86 instruction set is relatively simpler since the encoded form has a very regular structure. You can optionally use 1 to 4 bytes to encode the prefix. The opcodes encoding requires 1 to 3 bytes. You can optionally use 2 additional bytes known as mod RM and SIB bytes to encode the address of operands. If the memory operand uses a displacement, we can add 1 to 4 bytes for encoding the displacement after the SIB byte. Lastly, the x86 ISA accepts 32-bit immediate values, hence we can use the last 1 to 4 bytes to specify the value of an immediate operand if required. Okay, I will end the stream here. I don't know when I would do the next chapter because I'm getting quite busy with other things. But I will try to stream RISC-V as soon as possible. That seems to be in the next chapter, right? Wait, let me see. Yeah, the next chapter is RISC-V. So I will end the stream here, and whenever I get the time, I will stream the next chapter. Anyways, see you guys next time. Bye.